share the screen. Okay, ladies and gentlemen, today we are lucky for have Dr. Max to give his talk on geothermal basically, and then multiphysics method maybe that he will cover. So on behalf GSM and then also University Kebangsaan Malaysia, I'm hope that basically this topic will trigger everyone, especially on energy transition. Everywhere we talk about energy transition, Dr. Max. So I'm really hope that Dr. Max can spend his time and then all the participants have a comfort time, because normally we conduct in the morning. So today we start to make sure that Dr. Max also okay, even now already 9 p.m. At his place. So I don't want to waste his time anymore since already 4:02 p.m. Dr. Mac, let's start, and then you can add on some introduction before you continue with your topic today. Please welcome Dr. Max.
Yeah, I will do that. Yeah, good afternoon, assalamu alaikum everybody, and good morning if you are in Europe or America. I am honored to be invited to give this talk. I spent the last 15 years in Malaysia working for Petronas, and we developed many for hydrocarbon exploration, relevant to new energy. So what I will discuss with you today will also be applicable in geothermal, hydrogen exploration, environmental, mining. You name it is used in medical imaging as well. So I would begin by thanking Professor Haruri and UKM in particular for inviting me to share my experience, and GSM for all their support in making sure that I help download knowledge to the young people. I hope there will be young undergraduates, postgraduates, or researchers in the team who will be to gain something and carry on in the same way that I've done in the past and be successful. So I started off as a geologist, a degree in geology, first class honors. I have an MSc and DIC in geophysics from College London. I have a PhD in geophysics from Edinburgh University, and I also have MBA finance from University of Leicester. And I started off as a lecturer in January 98 in Leicester, as a lecturer in geophysics. I moved on to senior associate professor reader in environmental physics in Lancaster until 2008, when Petronas came to ask me to come to Malaysia and set up Multiphysics. So I was also the chair of hydrology panel for European Space Agency in Rome, ESA. I became team principal in Malaysia in 2008, and then custodian assessed in 2021. Whilst in Malaysia, I established physics ruler, which is a career progression kind of path. I built the multiphysics technologies and led to their growth in Petronas. We established Petronas #1 in the world for multiphysics imaging while I was there. So that's a very big development. I also trained a lot of people, more than 15 PhDs actually, 4 postdoctoral and over 40 master students that I supervised in my career. And I founded a new company just 2 months ago called Geo-Decisioneering Limited. I'm based in Lancaster, UK, focusing on environment, energy, and developing technology and training people, human capacity development. So do not feel left out. Students should write to me, ask for ideas and assistance, or give me something to do for them. I've written so many papers, more than 160. I've stopped counting. These are all in top journals: Nature, Geoscience, Reviews of Geophysics. I've won awards, many awards. United Geophysicist of the Year in 1996. I won the EM Global Prize, called the Gerald Homan International Prize for Excellence in Electrical Geophysics in 2002. I featured in TV programs, the best being the National Geographic Channel, which you can find on volcanoes, 2007. I was awarded Chinese government prize in 2012 for what we did in Tibet, where we actually showed the main cause of the sort of earthquakes that you have in the area. And in 2019, we got the Reginald Fessenden Award, which is the equivalent to a Nobel Prize. We don't have Nobel Prize in geoscience because of the multiphysics technology that we developed, which I'm going to talk about today. So I hope that will inspire young ones. Nothing is impossible. If you set your mind to achieve anything, you will achieve it. So if I could make it, so can you. So do not be intimidated. Everything is, and I'm going to try and guide you in a way today that will enable you to actually meet those dreams of yours. So my talk is actually distributed in 3 parts. The first part will cover the basics of physics, integrated geophysics and geology that are called multiphysics. The second part will show examples of applying the multiphysics technology to geothermal resource exploration, specifically from Indonesia and Malaysia, which is to you. I will focus on understanding concepts, conceptual models, and then the discussion session is really tailored towards prompting students to think, what is the next challenge? As we are now in energy transition, what do I do? What do I contribute to help the world reach its net zero target by 2050? We want to actually have a safer environment, cleaner environment with very reduced emissions. How do I get there? And I will talk about how I can assist in training people in Malaysia. And basically, I'm kickstarting the first part of my talk. Basically, I split it into modules so that it becomes easy to understand. So I look at the meaning, the rationale, or the context and scope of multiphysics. What do we mean by multiphysics? Now, the rationale. Most of the oil fields, most of the oil and gas fields that existed have been found. The ones that we're looking for now are very difficult to find in deep water, complex environments. And in addition, we have these global climatic changes, so-called global warming is driving a transition from fossil fuels to carbon energy sources. And therefore, things like native hydrogen, geothermal resources, wind energy have now become the new energy. And that includes lithium, because you need lithium for your batteries, for electric cars. So these are within the means of geoscience. And we should prepare ourselves for this new energy. We cannot be left out. And that is what this talk is about. I'll try and give you hints, ideas, so that you start to think in the direction of the new energy to meet the energy transition. Now, in this era, the geology that we're looking at is very, very complicated. It's not simple layered earth anymore. We're working in thrust beds, fold beds, areas where geology is very heterogeneous, and therefore no single method can give you all the answers. You need to be able to combine geology, geophysics, environmental modeling to be able to increase the accuracy and then reduce uncertainty in the predictions that you make about the subsurface. That is at the heart of multiphysics imaging. So the context of multiphysics is simple. Geology and geophysics are an essential combination. If you integrate, you get better understanding of the physical-chemical changes. That is the geological, the geochemical, and also biomedical biological changes in the subsurface. We use the phrase multi, many, more than one. If you are dealing with seismic, for instance, velocity is just one parameter. But if you are measuring velocity, density, magnetization, resistivity, radioactivity, etc., That's multiple parameters, and therefore that is called multiphysics. If you're dealing with seismic only and you measure compression wave velocity, BP, and shear wave velocity, the physics is the same. So a single is not multi-physics. You need to add something to it. When you add something extra, then we say it's multi-physics. If you're dealing with only electrical resistivity, for instance, and you're measuring it using different arrays, Schlumberger, Venner, dipole, you are using the same physics, but you are measuring different configurations or electrode arrays, and we say it's multimodal, so modality, multimodal acquisition of geophysics. Officially, in computational world, in computational physics, multiphysics basically is the study of multiple interactions of phenomena and involves solving many differential equations which are coupled, but many of those processes like wave propagation, seismic wave propagation, electromagnetic propagation, gravitational attraction are not related. They're different laws. Rules are very, very different. There's no common electromagnetic sort of diffusion and seismic wave propagation. So you cannot just simply link them, integrate them together based on physics. But in 2003, myself and my student, former PhD student, Luis Gallardo, invented the cross-gradient method. So that method is mathematical. It forces or it couples all systems, be they chemical, biological, geological, you name it. So it now allows in so many different things in geoscience, in medical imaging, in paint industry. So it is the biggest thing that has happened to geoscience. It's a game changer. And that's what I'm going to be sharing with you. That's the technology behind all the work that I've done in the last 20 years or so. So if you're you will be conversant with seismic velocity. So seismic reflection, seismic refraction units, the methods we use in oil, natural resources exploration. However, you can actually measure other parameters like density, which is how heavy a rock is. If you take a lump of sandstone and a lot of basalt and measure their weight, their density, the basalt will be heavier than sandstone. It would put it in a beaker of water, displace. It will actually, if you measure the volume of water displaced, so you divide the volume of the material by the displaced, you get a density. You find that basalt is heavier than sandstone. So on that basis, when you walk around with a gravity meter, you'll find that where you have sandstone, you have less attraction compared to where you have basalt. So we're able to be attracted to the earth if you have a feather or a leaf, it will be less attracted compared to you, human. If you jump up, you're heavier than a leaf. So your gravity basically is more anomalous than that of a leaf. So we can distinguish between sediments and basement rocks because of the changes in their density. If you also think in terms of magnetic ability of a material, rocks are magnetic, especially those that have magnetite, mineral, compared to rocks which are clean, something like quartz. So you can distinguish between quartz-rich rocks and those that are rich in magnetite. So that is the reason why we have ferromagnesian minerals, also felsic minerals. So your granites will be different from your basalt, your dolerite, and that is because we can distinguish the magnetic properties. Another property we use is electromagnetism, the ability to actually conduct electric current. So you pass voltage from two electrodes onto that rock. If that rock is rich in metals or metallic elements, it will conduct electricity. If it's full of quartz, silicon dioxide, it will not pass electric current. It resists the flow. It's a resistor. Yeah, geothermal energy we're looking for. The cap rock is full of shales. They will be conducting electricity, but the source rock Your granitic intrusion is resistive, so it will not pass current as easily as the cap rocks that are full of clay, montmorillonite, illite. And that is the method we call electromagnetic method. So I will be using mostly electromagnetic combined with seismic and density for geothermals today. Now, I don't know if my picture is blocking the slide. Can you see the full screen? Because I'm not. Hello? Anyone? Are you seeing the full screen?
Yes. Yeah.
Yes,
Full
Dr.
screen.
Max.
Okay. How do I? Mine is kind of blocked. Let me see if I can minimize this. Okay, good. That's excellent. Okay, so in this diagram here, I have a sketch of a typical igneous intrusion. When it intrudes sediments, it's actually rich in fluids. That fluid carries minerals, and it will actually form clay type material. So it's smectite, and that's where it also deposits its gold. You find that this igneous body will be rimmed by nice metallic mineral. Looking for gold, silver, platinum, this is where it will be deposited. And by doing so, it creates like a halo, a geochemical alteration halo, which is rich in metal, and therefore it has low electrical resistivity. It's called a conductor. It conducts electrical current. In here, the stock is more resistive. And therefore, we can actually map the stock based on a property called electrical resistivity. We can map the clay cover using electrical resistivity. The stock will also have different density compared to the basement that was intruded. So you could use density for that kind of thing. Area here will be cracked because you have water or fluids, hot fluids. It has high porosity. It has high water content. And the method or the parameter that responds to that most is electrical resistivity. Seismic velocity, on the other hand, maps the structure, the geometry of the layered cap rocks are best imaged with seismic. But the container, what's inside the container is best imaged using electromagnetic and density. And therefore, when you combine seismic or microseismic, resistivity, and gravity, you are in good for geothermal. If you're going to be doing hydrogen and coal, platinum, you name it, rare earth element, lithium, that combination to use as well for this reason. So there is a physical basis for in particular methods depending on what you are looking for. So if I'm interested in subsurface structure, science has the best resolution capacity, followed by ground perimeter. If you're looking for water content or mineralization, it's electromagnetic and electrical methods. Induced polarization. If it's talking about fracture zones, Vogler systems, is density and electrical resistivity. So that is the physics or the physical process behind the selection of particular geophysical methods for our geological problem solution. Now, it's important to understand how things are linked. For the benefit of geologists and geochemists in this meeting, think about intrusive body. Say calcaline intrusive, granite intrusive, diorite intrusive. It's altered the rocks because it's hot temperature, so there will be thermal metamorphism. You have your aureole surrounding it, and you have minerals that are being deposited. As this body is hot, so things are diffusing out of it. The rocks around it are cracked. It's lodging minerals in every fracture zone that you can find. In the same way, the chemistry is altered. So if you go out and you sample, you have an organ deep dig about 6 centimeters or 6 meters, take some rock samples, or you measure the soil gas, either the inorganic geochemical or organic geochemical measurements. So you do your methane, hydrogen, or your platinum, chromium, you name it. You actually find there will be a change in the chemistry as area of intrusion. The chemical compositions that you measure per million. So you have huge chemical anomaly there. If you do your geophysics, you also find that geophysics will change proportionately across this geothermal field. So this structure is called a geothermal trap. It is not sealed perfectly, it's always leaking, and that's where the seepage will interact with the chemistry of the overlying rocks, alter that, making the overburden to have anomalies that you can sense using direct and indirect exploration methods. So your geochemistry and your geophysics can be linked via the overburden. So I will show an example in the next slide. I use an analogy from oil industry. You have your oil trap. The oil is capped by a shale layer, but it's actually fractured, and it allows seepages, and this get to the top of the earth, so at a sea bottom or ground surface. You find a bacteria colony develops because they actually metabolize this. They generate energy by consuming these seepages from the ground, from the oil field. So that becomes a harder ground. So if you measure the resistivity, it will actually show an elevation over the oil field. If you also take specimens every few meters and you do measure the number of count of bacteria in that sample, you'll find that the population will actually become much higher over the area where you have your chemosynthetic community. So that is the basis of using geochemistry or microbiology to prospect for oil and gas. There's a correlation between resistivity and the most probable number of bacteria counts in the oil field. So that's another way of establishing a linkage between chemistry or biochemistry or geochemistry and geophysics resistivity. On the other hand, if you have a seismic image over an area where we have gas seepage, have methane, CO2, hydrogen sulfide or hydrogen being basically seeping through fractures, you'll find these pipes, which you see clearly on your seismic reflection image. So pipes 1, 2, 3, 4 was actually investigated using marine CSEM method by Nigel Edwards in 2005. Here you see the resistivity as the ship was being towed past these pipes. They have a high, another high, another high, another high corresponding to those pipes. That means that there is a link between what you're seeing with your seismic, this image, and what we see with measurements of resistivity using electromagnetic method. So clearly you see that you can tell that there's a working petroleum system, a working hydrogen system, or a geothermal system there. So there is a linkage. All methods are connected. Geoscience is all embracing it. Merges geology, geophysics, biochemistry, you name it, into one. And that's what we do in multiphysics. So what is the scope of multiphysics in the new energy transition? This is important for students of geology or geoscience because we're heading in a different direction now. The classical geology that trains you for oil field, oil exploration, solid minerals, is actually going to be a little bit modified because we're living in a world where there's pressure for us to clean up the environment. We have global warming, and every country is making every effort to actually meet the Kyoto agreement. By 2050, we will have a net zero emission, net zero carbon dioxide emission. And that means that if you are producing oil and gas the classic way, you have to modify it. So in here, I have this triangle pyramid that shows what we normally do when we're looking for natural gas, which includes like hydrogen, CO2 storage, and some oil. First, we need to get a block in a basin. We'll find a basin, Sarawak Basin, Sabah Basin, Santos Basin in Brazil that you want to play in that basin, you need to find a favorable location where you have your source rock, your reservoir, and your cap rock in place. So that is called a plane. You want to ask yourself, is my block in the right place to capture charge? If it's not, don't take that block. So you need geophysics or multiphysics, G and G integration at that stage. Once you've selected your block, you need to identify a prospect. Once you find a prospect, you need to cope with the geological complexity. How do I image this structure to know where to put my well? And when you've done that, you want to predict the kind of fluid in the container. Is it oil? Is this gas? Is it hydrogen? Is it CO2? How good is the seal? We want to know that the seal is intact because we now have a commitment, the Kyoto commitment, that if you're extracting oil, make sure that that container is good enough so that you can sequester or bury CO2. When you've taken the oil or gas out, you put CO2 back into the system. So we're not just extracting oil anymore, we're actually recycling the carbon dioxide, we're burying it. You can use it to actually enhance your production initially to force more oil out into a collector well, but ultimately you'll be burying CO2 in the ground. You want to ensure that the seal is not fractured. If it's fractured, do not bury your CO2 there. It's like trying to pump a burst balloon. We don't want that. So geophysics has critical role to play in the energy transition. And there's also a question, if you're burying CO2, is the seal good enough to last 100 years? The CO2 must stay in place for 100 years. That's a Kyoto sort of requirement. So geology has taken a new dimension. It's not just finding oil and gas. And all these are expanded upon in a recent article by Meju and Saleh, 2003. The reference is here. If you can't find it, let myself know. I'll send you the PDF of the paper. Geothermal and hydrogen, the new energy that we're talking about today, also can be explained in the same context. Initially, we're looking for screening areas, Sabah, for instance, onshore Sabah, screening areas to find where we can find features that might contain hydrogen or geothermal. And then we'll look at the deep structure to see whether we're able to actually drill safely and find the reservoir. And then you have to predict the composition of the fluid. Is it fluid dominated? What kind of, is it partial met? What are the flow and thermal conditions? Can I produce from it? And if you're developing your geothermal, you want to actually do your well aquifer performance test and also monitor the aquifer. You want to enhance production by fracturing the rock, but you also want to bear in mind that the ground will subside when you start to produce, and you have to think in terms of sustainability. I would show you an example of how I would consider sustainability. Do you have that resource available for the next millennium? Or am I just producing it and that will be the end of it? We're not looking for those that will not last anymore. We're looking for sustainable resources. How do we guarantee that we can actually say something about sustainability? That is what multiphysics does. So multiphysics evolved out of the need to actually have more precise answers. Before, you use one method, seismic, but you cannot find answers from one method. If you integrate geology, geophysics, you maximize accuracy, you minimize uncertainty in a shared world. And that leads to a very consistent, a very solid or robust working model for your resource and for your surveillance system. And once you've gone through that stage of combining so much information to take decision with data, we say that you've rationalized your portfolio and you are creating value. So I would, in my talk, I'm going to be coming back to these phrases: portfolio rationalization and value creation. It's important to understand that. First, I'll guide you through the technologies that are available for acquiring multiphysics data. We start with airborne methods which can cover large areas easily and fastly without having to have permission from all various landowners, as you do when you're doing ground studies. So you can fly aeroplanes that carry sensors that will measure gravity, radiometrics, and various other parameters. It has a system. This is the Fugro, the Falcon system. It has a magnetic sensor. It has a laser scanner. It also carries a flux gauge magnetometer, has a radar altimeter, and this is the gravity radiometry system, radiometrics to show what is radioactive or not, and a digital GPS. So this is a full multi-physics system. It's making multiple measurements along its path. We have the Bell Geospace that measures full tensor gravity and also magnetic data. So these are systems that any undergraduate should be aware of, or any practicing geophysicists should be aware of. For multiphysics, it is applicable to geothermal, microseismic, and EM and gravity are the key tools for geothermal analysis. Electromagnetic is split. It has so many different methods. There's one called control sources, control source electromagnetic, so artificial source electromagnetic, and lightning, the one that uses lightning discharges, magnetotellurics. So I will be using or showing examples where we've used those two. Now, this can be used on land, it can be used in marine, and you can also make airborne electromagnetic measurements. The same instruments can be used to measure microseismic activity and EM activity. So a company based in Houston, KMS Technology, also manufactures, I took this picture of this website, they manufacture these systems. So they're available and they can be deployed quite rapidly. This is the example of the set that was used in a recent acquisition in Thailand. So these are electromagnetic and microseismic measurements. These systems have 200 channel wireless receivers, so you can actually make a lot of measurements using the KMS system. There are other vendors too. Phoenix Geophysics manufactures MT systems for land use. And typically for MT, you would lay out electric lines in that direction, north-south and east-west. So those will be grounded at two ends. You have porous spots as your electrodes, and then you will lay out magnetic sensors in north-south, east-west, and then another one in vertical direction. So that's what we have here. You have, it's called the HX, HY, and HZ, 3 components of magnetic field and 2 components of electric field. So if you divide the electric field in the north-south direction by the magnetic field in the east-west, you get what we call electromagnetic impedance, just like you have your seismic impedance. It allows you to define resistivity in one direction. If you divide the electric field in the other direction by magnetic field in the orthogonal direction, you get a resistivity or impedance in the other direction. So we call this a full tensor system because you can mathematically rotate the measurements to define resistivity in all directions. If you're a geologist and you looked at a thin section under a microscope, when you rotate your thin section under a microscope, it changes in intensity. The light changes. We say it's pyrochlorism, or birefringence. It's because as you rotate, the light will basically focus better in one direction compared to the other. So when you are in one particular direction, the light is split and it's basically shining in strike direction or in the deep direction of the mineral grains. So electromagnetic measurements can be rotated to actually map out geological strike or dips in the subsurface down to the mantle. That's what MT is all about. You can do the same in the sea, and when you do that, we call it marine MT or marine CSEM. And EMGS is a company that measures marine CSEM and marine MT quite well. Now, what is important here is that if you are going to be looking for specific things relevant to the new energy, for instance, if you're going to map caprock shale, for instance, or you're going to inject surfactants for enhanced oil recovery into the ground or brines, or you're going to map shear zones to check the integrity of your cap, you're better off using magnetic source fields. If you're going to monitor resistive reservoirs, geothermal, hydrogen, hydrocarbons, or to store CO2, or look at water alternating gas injection, you're better off using electric source fields. So these considerations should be borne in mind when you are deciding the best possible scenario for your investigation. But once you've collected the data, what I've shown you are collection systems. What do you do with the data? That is the biggest question. How do I manage my data? And that's at the heart of my talk. How do I make better decisions with my data? To begin with, you've collected data from so many different equipment, so many different things. You need to find a way to homogenize them, put them on the same level. How do I homogenize them? And once I homogenize the data, how do I then produce a geological model of the Earth from this data? So I'll be guiding you through the journey of being able to find a way to merge any kind of data. Any kind. You make your rules, you make your own laws, like I did. And once you've homogenized your data, you then look at the other scenario where you have physics that are different from seismic, physics different from electromagnetic or resistivity. How do I make seismic talk to electromagnetic? You can either link them up structurally or petrophysically. I'm going to guide you through how I did it in my time successfully and how I still continue to do it. This is very important. So, in geophysics, if you're doing geothermal work, you would have been using electrical current, DC resistivity, where you are pumping current into the ground and expanding the length of your arrays. So your electric line, you start off with a few meters, tens of meters, 20 meters, your arrays going geometrically expanding, because as you expand, your current path goes into deeper and deeper earth. So when that is expanded, you're sampling more and more volume. So you're achieving probing depth by increasing the length of your electric dipole. That's geometric sanding. In the same location, you can keep the array fixed, the length of the electrode fixed, but pass current, alternating current through a piece of wire and just change the frequency of the current. As you vary the frequency from high frequency to low frequency, you're actually imaging deeper and deeper and deeper. So by changing frequency or time, or by changing length, distance, you're going deeper and deeper and deeper in the electrical and electromagnetic methods. All of these are measuring one parameter called resistivity. Now, electrical methods that depend on length to get into deep positions in the earth are related to methods that rely on frequency or period. 1 over frequency is your period. So time and space are related via this property called electrical conductivity or resistivity. 1 over conductivity is your resistivity. So all this thing in bracket is constant number for any depth interval. You go to a different depth, resistivity changes, but this is true. I is a constant, mu naught, magnetic permeability of free space is a constant. those numbers don't change. What is changing is the resistivity at different depths as you go from sandstone to limestone, for instance, or carbonate. So this thing, the equation basically is equivalent to T is equal to a constant times L squared. Look at Einstein's this popular equation, E equals mc squared. Everybody knows that. Somebody, can you please don't it? Somebody is talking in the background. So E is equal to mc. Remember this equation, power law relationship. The same thing applies in the earth. So that equation is similar. It allows us to actually link time and space in geophysics, and it works. And I encourage everybody to try it. I've used it over the years. It's used globally. But there are many methods that don't link up easily. Seismic velocity and resistivity are not connected by any relationship. These ones are connected because it's single physics, the same physics, a single domain, resistivity measurements. These ones are not. So for this, we need to find a way to make them link together. And that is what I'll come to that. That's what this technology called cross-gradient is all about. For the single physics that are linked, it's easy. If I measured my resistivity using DC resistivity, Venus, Lumpur array, or IP, and I use time domain or transient EM measurements in time and magnetotelluric in frequency or time, you can relate them by using that equation that T is equal to this constant times length squared. So you can convert DC length into frequency like I've done here, or you can convert MT period into length. So this applies in any environment. And I encourage you to do that. So if you don't have software for DC, TM, for everything, you can actually convert data from one domain into another and have a qualitative interpretation. That's how you can merge so many of these electrical and electromagnetic data sets. So it is possible. It's not difficult. You can do that. Once you homogenize, it becomes easy to apply any transformation, any inversion. You'll be able to work out a model that matches your data, both the time domain data and magnetotelluric or IP, any kind of data sets for electrical, and so long as it's single domain. The hardest one is when you are dealing with data from different domains, seismic imaging, electromagnetic imaging, or magnetic imaging. Those are very different. Gravity and seismic are connected through density, but magnetics is not connected. Now, gravity and magnetics are connected, pattern of transformation. So the hardest is electrical resistivity and velocity and magnetic susceptibility. Combining those three are difficult in geophysics. How do we do that? We can use this technology called cross-gradient joint inversion. What is it? I am going to spend some time here for my geologist colleagues, geoscientist colleagues. Please listen to this. It's very important. I want you to actually take this away with you and be confident that you can actually make discoveries, your own discoveries. You don't need to be Einstein to do so. Look at a hypothetical scenario. I have a system. This image shows massive sandstones interlayered with shales. So look at that. So sandstone shale sequence. This sandstone is drilled. I drill a well, hypothetical well. In this well, I make well log measurements, or I log the wells. So in this red ribbon here, I have resistivity log. So the sandstone is more resistive than your shale. So at shale, it goes lower. Sandstone, massive sandstone, high. Shale interval, it drops to the left. Sandstone, it goes to the right, and so on. So here is clay. Clean sand, it goes to the right. Shale, it goes to the left. If I measure gamma ray, radioactivity in the ground, it will follow a pattern that is opposite that of your resistivity. If I measure density in the ground or porosity, it defines a pattern as well. So these are called are well logs. Now, this well was logged on this geological medium. So all these logs refer to the same geology, the same thing. So there's a common reference, the same geology. So these logs are nothing but numbers. So here will be 10 ohms, 5 ohms, 2 ohms, 10 ohms. So it's a series of numbers as you go deep down. So it's called, therefore, a vector. What is a vector? Something that has magnitude, the numbers, and direction, depth. So that is a vector of resistivity measurements, a vector gamma ray, vector of porosity measurements. Now, these vectors are measuring the same earth, a shared earth. In mathematics, we say that these vectors are therefore parallel because they are measuring the same well, the same earth. So we use this symbol, double. If you look at the way it changes, the gradient, the way it changes with depth, if you take the derivative, the gradient, we say that the gradient of conductivity or resistivity is parallel to the gradient of density. We're dealing with the same system. Now, from mathematics, any two parallel vectors, the cross product of those must be equal to 0. By the way, this gradient is written in Greek shorthand just to make life easy. Greeks find ways of writing things to simplify things. So that gradient is that grad is represented by that symbol. So grad resistivity is parallel to grad density. This well situation because we are referring to the same earth. And therefore, the cross product of this grad resistivity and grad density must be equal to 0. It's a law in mathematics that the cross product of two parallel vectors is 0. This is well known. What we've done in our cross-gradient technology is to say, okay, we are searching for, I've measured seismic, I've measured electromagnetic data, denote seismic as 1, denote electromagnetic as 2. So data seismic travel times. Data 2 are resistivity measurements. I want to find a resistivity model that obeys the same law as the seismic in the area, bears the same geology. How do I do it? You want the two models to identify the exact geology. So what you do is you pose the problem as, oh, gentlemen, talk to yourselves. So you seismic, you electromagnetic together. You are guided by regularization, an initial guess. We don't know what the model is. You guess what the model might be, reference model. We impose you want it to be very smoothly varying. That's what we have this regularization. But they must obey the mathematical condition that the cross product of resistivity and the cross product of velocity must be 0 geological boundary. So at that boundary here, it has to find the correct turning point, the correct turning point. That is the meaning of this equation. It looks complicated, but it's not. It's actually very simple. That you're doing your minimization or your inversion. You're searching for the best model that explains your seismic and electromagnetic or gravity or density or magnetic data with this geological condition that the two models or there are 10 models, all models must satisfy the condition that we know from well logs that the gradient of density, gradient of velocity must be 0 at major geologies. This is the cross-gradient method. That's what it is. It's a mathematical thing that resolves conflict. So the models will not be different from each other. We say it's actually in accord. They are in accordance. There's no conflict. There's no rest. They are resolved. So the mission really is to produce models that are geologically realistic. They are more accurate. They're meaningful, and they create value for the owner of the data. So we published 2003, and since then, there's been more than 400 papers, articles written by other people, and in 2019, we were awarded the Regional Fessenden Award by SEG for this a new disruptive invention. And this is now being used in medical imaging in so many industries. It's amazing. So please try it. You can use anything you want. You can make anything you want if you understand what we're doing. So this is exactly what the cross-gradient technology is about. Look at a scenario, a hypothetical test. Say you cut a synthetic model for an area where we have stone, thick sandstone, limestone, carbonate, followed by basically a sandstone layer and then shady layer, intruded by granite. So that granite in geolocation is discordant. The layers of rocks are concordant with each other. If you compute the velocity of sound wave through this structure and the resistivity propagation through this structure, you will find that when you invert the synthetic data for seismic separately and you invert the synthetic data for resistivity, this is what you get. Look at the seismic. Seismic picks up horizontal boundaries perfectly, better than any method. It doesn't see discordant features. So that's the inversion. It's actually incorrect. It says the basement is flat. This is the basement. The granitic material, this is your basement here. It doesn't say it. Your resistivity measurements set discordance better than seismic. It sees discordance, but the layerings are not as resolved as seismic. So there is a confusion here. It's conflict of interest. We say there's an issue here. We have conflicting models from separate seismic and separate resistivity inversion. When you apply cross-gradient method, the results are different. The results now allow resistivity to let seismic borrow from it and seismic to lend support to resistivity. And therefore, we end up with velocity that is layered, plus it shows this discordant intrusion. The basement is well resolved, and so is the resistivity method. So these two are now in agreement. The conflict is resolved. So I call it the mathematics for resolving conflict. This is the true geology. It actually shows the true geological structure better than that. So now you can talk, now you can discuss confidently that we have a proper geoscientific model. It's the technology called cross-gradient. And the way it works, the way we do it for joint seismic and resistivity inversion, the classic one, 2003, 2004, we will start with the half space. We assume we don't know anything about this, the velocity, we don't know anything about the resistivity. And when we iterate, iteration 1, 2, 3, 4, as you iterating, the misfit is decreasing chi-square. Once you get to a chi-square of 1, normalized chi-square of about 1, we stop. So I'll show you this model when it has statistically reached a place where we accept the misfit. If you plot the model in color, you will see that the velocity tomography is shown there, the resistivity tomography is shown there. This is for the environmental study that we did. The depth of interest is about 40 meters. Look at these features. Look at zone A, zone B, zone C, D in seismic and in EM. They are identical structurally. We did the same with CSAMT, control source electromagnetic frequency magnetotellurics, velocity, resistivity, and velocity. Look at A, B, C, D. All those features are imaged by MT and seismic, and also by DC resistivity and seismic. That is conflict resolved. That is the way we do it. That the two ends of the spectrum are talking to each other. Now, there's a beautiful thing that follows from this. Once you got a model that satisfies geological conditions, you can then see how they correlate. So you take a resistivity measurement or velocity number there, take a velocity at that point. So you sample pixel by pixel, pixel by pixel, everywhere in this model. Cross-plot the velocity and the resistivity. So if you plot them in different colors for those different areas, if you're sampling through area A, B, C, D, you will find that they define different clusters. So this graph here shows a trend for a particular segment, A, B, C, D. So it means that you are decluttering, you're basically interpreting facies or horizons that have trends in reciprocity and velocity. And those will be your facies, hydrofacies, or your hydrogen facies, or your geothermal facies, or caprock facies. That is the beauty of the cross gradient joint inversion. And that's what I'm going to use in the example in the geothermal case study that I'll share with you. I've shown you so far two methods combining seismic, and you can add anything. You can have resistivity, seismic, gravity, magnetics, porosity, microseismic, anything can be combined. If you really want to dive deeply into it, look at the article published in Reviews of Geophysics in 2011. It has everything for fusing end property. You can fuse geology, crop maps, LiDAR images, everything is possible. And when you do that, all you do, that equation I showed you before with any components. So you have your data, so you're minimizing misfit between your seismic, gravity, magnetic, you name it. You're smoothing it, polarization. You're then forcing them to obey cross gradient. And if you have a prior information, you can add it into the mix. So you can integrate. So this is G and G integration. And this was implemented in a software called RLM 3D by CGG. And it's available off the shelf for anybody to actually have a license. So you can license it from CGG Milan, CGG Multiphysics. So when you have small scale surveys, fine, you can do that. You have large scale, you need a supercomputer to do with analysis. But there are other data sets which are not easily jointly inverted because of computational limitations. If I have a huge area, I have 3D seismics. Don't forget, seismics are measured every 6.25 meters. The hydrophone is stored and you're making measurements every 6.25 meters or 11.5 meters. So you have so much, you oversampling the area. If you want to invert all that lot data, you meet with difficulty unless you have a supercomputer. For normal university, normal companies, you don't have that kind of access. So you need a medium-sized computer and you want much out of it. One thing you could do is you can take the seismic volume and then ask electrical methods, gravity methods, or magnetic methods to obey that volume and keep all this typically interpreted in terms of horizons. You find horizons of interest. In this case, this is a truss system. You can also use your horizons, keep them fixed, and use them to guide your model building. But that depends on the person that is picking the horizon. So it's subject to human error. We don't want to have people influencing the interpretation of horizons. I give the same data to two geoscientists, they will pick different horizons. How do you remove error, uncertainty? You can actually use a 3D volume, skip horizons, just basically compute something called structure tensor and cross gradient the seismic image and resistivity image. And that's what was done in the classic paper that we wrote in Interpretation 2020. All it is you take that seismic and you compute structure tensors and store them. Those structure tensors will keep all the structural dips. You can see all these dips and sort of where changes happen. All those will be kept in the. You then say, okay, CSCM or MT or gravity or magnetic, use this information to find models that are structurally consistent with seismic using the cross gradient method. So when you do that, you write it in an expanded way like this. I've got my data sets, which will be my gravity, my magnetic or electromagnetic data. I want my data to resemble the seismic structure tensor. This is not to be changing. This is fixed. So again, the model you're looking for, you keep coming back to make sure that cross gradient between your seismic tensor and the model you are searching for must be zero. So you are forcing your model obey your seismic structure tensor. This thing here is computed, is fixed, it's not changing. So you're not using so much memory anymore. So the memory is spent on this side, which is fitting the data from electromagnetic or gravity or density or induced polarization. So that way you can benefit from seismic structure without inverting the seismic. So you save computational costs. So it's a nice way of solving large volumes of data. It's an example where it was done once I was in Petronas. CSM MT were acquired in everywhere when you have these red dots. And this example will use only CSCM from the blue area, but MT from the red area, but showing with seismic such a tensor for the whole area. So the inversion was done in stages. First, MT was done. You could see the MT is structurally conformable. By comparing it with horizons picked manually, these were not used in inversion, just for comparison. You could see that MT resistivity is conformal to structure. Okay. You do cross-gradient inversion, in which you actually use the cross-gradient of resistivity in horizontal and vertical directions. We say resistivity is anisotropic, so you measure resistivity in the vertical direction and resistivity in the horizontal direction and say, okay, oh, gentlemen, talk to yourselves, be structurally conformable with seismic. And that's what you use this cross-gradient method for. So when you do that, that's where you end up. You can see that the horizontal resistivity is actually structurally conformable, and so is the vertical resistivity. Where we have a well, you look at the horizontal resistivity versus well log, that orange line shows that the horizontal resistivity is actually going through the average value of the well log. So it's actually computing the resistivity correctly. So cross-gradient allows you to do so many different things. You produce models that are geologically robust, geologically consistent. If you take that model that we computed and overlay it on seismic ESDM data, you actually see how structurally conformable it is. We did inversion by keeping horizons fixed and compare that, and you can see that they're very similar. But that involves so much effort. That involves human intervention, picking horizons. That is just structure tensors. You don't have any need to pick horizons. It's automated. So we have similar results, and you reduce interpreter's bias because anybody could pick different things as their horizons. So that is basically end of my first part. And is there any question before I move into the second part? Any question? Any question? The second part is very interesting. Thanks, for
next, Mr. Max.
Yeah.
I want to stop you for 1 minute, for 1 or 2 minutes.
Okay.
Maybe you want to take 5, maybe take a break.
Okay.
And then
if
we continue. Is it okay?
Okay. Yeah.
But here also raining, some lightning. So basically, is it okay for you to continue? You have another 1 hour, right?
Okay. I'm happy to continue if everybody's happy.
Okay. So please continue. Mr. Robin, I think you can ask maybe later, or you want to answer now, Dr. Max?
It doesn't really matter. But yeah, Dr. Harry, this is a very intense, what do you call this, presentations. It's very good, this cross-gradient multiphysics. Maybe later.
Okay.
The question?
No, yeah.
Okay.
Okay, thank you.
I will, the discussion, we will have lots of time to take questions as well. Okay. If I just continue, let me move this out of my way. Okay. Now, it's important to actually understand what we're looking for in geothermal exploration. We have volcanic associated, and then we have those that fault associated, Volcanic means, or magmatic associated, we have heat because you have an intrusive body. So you have a alkaline or igneous body, intrudes the ground, and these white contours are temperatures around the area that's impacted. You will find that. Okay. So you have this thermal gradient. Ideally, when you have fracture zones, water comes in, you have rainfall, or if you're in the sea, seawater infiltrates, and as it travels, then it gets heated up. And then you have basically fumaroles. You have springs of very hot water, steam coming out of the ground. So that means that you have a deeper hot source. So I want to be able to tap into that. Now, because of the temperature difference, we have minerals are changed around this body. We call it geochemical alteration. So you have smectite, argillite, elite, montmorillonite, and zeolite. So these areas will also be impregnated with gold. This is where you look for your gold. So your gold, your copper minerals will actually be deposited. So in Malaysia, cassiterite, your granite, all of them fringing this intrusion. So how do I image the structure, find where to put my well to produce water that is hot or rock that is hot? That is what this. Alternatively, if you have a shear zone, the ground has been broken by fault, goes deep. It's a tap water. Hello, so internet is unstable. Hello, can you hear me?
Yeah, Doctor.
Yes, we
Hello?
are on. Yes, we can hear you.
Okay, good.
Yes, very clear, very
Okay,
clear.
thank you. Oh, thank you very much. So if you have deep faults, they actually channel water up and down. And therefore, you're going to find that some areas will be much more hotter than the rest. And that's where you want to drill into to produce your geothermal energy. So we'll be looking at how we use geophysical methods. By the way, this also implies that there will be noise in the environment if you have hot water swooshing around. It will produce microseismic noise, microseism. That's why microseismic is a key tool for looking at reservoirs that are going to be productive. Here as well, you have micro earthquakes related to this intrusion and the aquiferous conditions above it. So microseismic, gravity or gravity, and electromagnetic, because of this argillitic shale or clay alteration. You see it easily on electromagnetics. Hot rock, you will see it will be resistive. So this is the geological model you always have in mind. In the same area, you have your local sandstone deposits. Those reservoirs will be filled with hot water. So sometimes the water will be maybe 200 degrees Celsius. You'll be able to use it for so many other things, heating and you name it. Or if it's just warm, you maybe use it for bath, hot baths. These are all of economic importance, depends on what you're looking for. You want hot rock for proper energy generation, you have to go. So how do we do that? How do we do that? First, you need to be able to know the expected geophysical signature of the various components of your geothermal resource. The clay cap is always electrically conductive. It's also electrically anisotropic. What do I mean by that? The smectite, your eolites, all these are minerals that have flaky structure. Biotite, phlogopite, you name it, these are flakes. So a pile of flaky minerals, they will conduct electricity differently if you come vertically or horizontally. So the flow path is easier along the bedding plane compared to across the bedding plane. So there will be anisotropy also involved in the clay cap. The reservoir is resistive electrically. It's also dense. You have your alkaline or granitic intrusion of metamorphosed sedimentary rocks. So it should be denser than the metasediments. So you have a density contrast. It will also have a velocity contrast. And therefore, if you combine resistivity measured using magnetotellurics or DC resistivity or induced polarization or spontaneous polarization, SP, if you measure gravity or microgravity, and you measure the seismic property, earthquakes, using earthquakes velocity, you will be able to find the exact spot to drill. That's how you use uncertainty. You don't want to drill here. You want to drill right there. So you reduce uncertainty, save money, you save the environment, and you save time. That's what we want to. So by doing that, you add value. You're not wasting money. You're adding value to your proposition. So this is similar to what I just told you here. So in the sedimentary, you have hot water. If you're in the intrusion, you have hot granite or something. These will be resistive. Your hot water in sediments will be moderately resistive. Your conductor, your cap conductive, you cannot fail to see this. This is a telltale. You must be seeing this in order to make a decision. If there's no cap, don't drill. I say this again. If there's no conductive cap, please don't drill. It's like you're looking for hydrocarbon and there's no shale layer above it. It's just sandstone that is open. How are you going to make money out of that? Do not drill if you don't find it, if it's not well capped. Please, do not drill. Case studies begin with Indonesia. If you remember, Indonesia, you have a subduction zone, so Java Trench. So something is good that it begins to melt. You have alkaline intrusion, rings or lines of intrusions, and these have created opportunities, myriads of opportunities for geothermal energy in Indonesia, and also hydrogen, lithium, a wonderful place to be. But let's focus on geothermal energy first. So I'm going to show you examples from there, and I will show examples from Borneo. So that's Indonesia there, Malay Peninsula, that's Borneo there. I'll use data from Sarawak, offshore Sarawak, and data from offshore Sabah. And I'll show you the implications for onshore Sabah and onshore Sarawak. The geothermal field of interest is Darajat in West Java. And this picture there provided by Chevron. So it's a Chevron property. And it's been over 40 years of exploration and 20 years of production in this area. And its productivity ranges from 55 to about 1,110 megawatts. So it has a combined output of 271 megawatts. And we have dry steam at wellheads. So a classic example of where you do MT, microseismic, and gravity. So data sets available. This was actually a job handled by CGG Milan using multiphysics software, RLM 3D, which incorporated the constraint. The data sets available are MT, gravity. So the red diamonds are gravity stations. So it's 3D coverage. The blue angles are MT stations, 3D coverage. And then here we have your micro earthquake receivers. And it's these are three component receivers. So you have 3 data sets. How do you combine them to find the right spot to drill? First, I'll show you examples where you do single separate inversion. You do only MEQ, microseismic earthquake, only gravity, to actually see whether they actually do the business. And then you use the cross-gradient technology to bring them together, to make them talk to each other. And this is the equation that basically is used, the cross-gradient equation. So your gravity, your micro earthquake, your magnetotelectonic sets, you are trying to find a model that matches your data, all your data, as smooth enough, and obeys the geological condition I explained to you, the cross-gradient property condition. And if you have any air prior information in the area, LiDAR images, topography, you name it, you can put them in here in your reference. In this location, they actually have porosity measurements because the wells have been in production for quite some time. So there's a volume of porosity that could be used as a scale image, fixed image, and you do cross-gradient image reference to a volume of porosity that is not changing. So let's look at single domain inversions. That is no cross-gradient. So we look at MT resistivity in the west-east direction and north-south direction. So you're taking a slice from the volume. And you look at the density recovered from gravity inversion in east-west and north-south. So you're looking at a vertical depth slice in 2 orthogonal directions. The well trajectories are shown by these black lines. What you will see straight away, and that is the top, it's like isothermal line, basically. So look at the resistivity images. We see a high resistivity body here, but it doesn't mimic this structure, this purple line quite well. It's there, you could see there's something there. So in the east-west and north-south. So MT is done quite well. Look at the cap rock. It's been imaged, it's there, it's kind of broken there a bit, so there's a fault there. Look at the cap rock image in that direction, there's a fault there, it's fractured, but it's sealed. It's important. Density, look at the density anomaly, it's actually offset, it's off where MT thinks that the intrusive body, the stock will be. Density places it over there. In the other direction, it's actually up there and to the side. What then happens when you do cross-gradient joint inversion using the technology? All models start with homogeneous hard space. That is, you don't know anything. You assume you don't know anything about the geology or the ground. Blank space. So this single domain inversion did not, just reiterate, did not do the business. But when you do cross-gradient joint inversion, look at what is happening. MT is doing what it's supposed to do. Gravity is now where it is supposed to. Look at that. It's exactly where it should be. So this is wonderful. So this is superior to single domain. So please bear in mind, if you're doing geothermal work, think in terms of joint inversion of gravity, magnetotelectonic, seismic velocity, because that's the way to actually remove doubt, make life easy for managers to take decisions. You can take a decision that, yes, the heat source is here, not there. That is the beauty. You create value, you reduce uncertainty, you minimize costs, you make them do the right thing. If you have porosity volumes, if you had a well before, or you have seismic reflection, and you calculate porosity, you can use this image and infuse it in the calculation. So use it as a reference model. And it's fixed, it's not moving. You calculate structural tensor and ask the joint inversion to mimic, to satisfy this image. When you do that, when you couple this external porosity volume to the cross gradient, bang, everything starts to fit. So look at that. So it obeyed the porosity volume. The density is in the right place and also obeys the porosity volume. The resistivity is in the right place and obeys the porosity volume. So by coupling an externally derived porosity model via Crossgradient, you basically are able to map the top of lava flows, which is shown by this purple line. So that is wonderful. That is the future. That's how to do it. You can then interpret. So that's what you give to management or the interpreters. You can then begin to compare with methylene blue, find out different parameters of heat, the quality, that's what I meant by the quality of heat and all those kind of things, the fluid compositions. This is what you then combine with geochemistry. You would have done fluid chemistry analysis in the area. Then you bring in all these together. This is G and G integration at its best. That's how to do it. In this situation, we find that the high values methylene blue mark areas of increase smectite clay, and that smectite clay is electrically conductive. So that is how it should be done. Bonio. I have the honor and privilege to work with Petronas for a number of years, and Petronas made a wonderful investment in offshore Saga. We acquired marine magnetotelluric and CSCM covering a large area, more than anywhere in the world. This is the largest single acquisition that I know of in my career. And the idea is to actually be able to understand the lithosphere and see how it impacted on the heat distribution, sediment distribution, and petroleum fairways, as well as heat fairways in the area. So I'll show you what was done while I was in Petronas, what I'm currently sort of working on. But in 2021, we actually picked a small area. This map here on the left is the heat flow from Maslan Medan and John Jung, published in GSM Journal, Bulletin of Geological Survey of Malaysia, 2021. I'm going to show you a result along this line, this black line, that one, that's passing through the longest axis. Is that one. So that's the resistivity. The color scale is reversed. This is the industry color scale. So red is resistive, blue is conductive. But you can see the cap. It's conductive, it's resistive. And this is resistivity. Actually, it's highest here. It stops in the middle somewhere there. It stops there, which agrees with the heat flow measurements of Maslan and Medan. So here is hotter in this area than there. So if I was going to drill a well for geothermal, I'm going to be talking there. If I'm going to model the generation of hydrocarbon, the heat source is going to be in this area. So that is the beauty of doing MT, NMT, with this CSCM MT 3D inversion. When you superpose that on reflection seismic, you actually see the area of high resistivity is characterized by very, very reflective. It's called ductile cross. It's partially molten. Ductile cross is hot. When the ground is actually very, very hot, it goes into, partially start to melt. So it's partially molten. So all these nice reflectors are because of the high heat flow in the area. So you can combine that with EM. And what you notice here, look at this shape. Look at that thing there. That is the shape of a basin or a sub-basin, a graben. That graben is formed because you have a heat source right at the bottom. That is Mackenzie's model of lithospheric, of basin subsidence or extension. So the heat source is sitting right at the bottom of the basin. So that is nice for anyone studying geology. Remember Mackenzie's model for basin evolution. The heat source is right at the center of the basin. How about on a regional scale? This is a summary of the Saba lines, which are those. And this green polygon here is that green polygon. The map behind it is Maslan, Medan, and Jung's heat flow map 2021. So high heat flow, high heat flow, high heat flow. This is this extension axis of South China Sea, high heat flow expected. So high heat flow. So look at our resistivity. Blue in here, because that's where you have your reservoir. Your heat is in that area. It has a nice cap, that reddish thing. So it's a nice geothermal system. A nice area for cooking your kerosene as well. So this is probably what drove the generation of your hydrocarbons. And it seems to be steeply dipping, and therefore, if you have fleets migrating from deep to the subsea. In this case, this would be the Northwest Borneo Trough. We do isotopic measurements, resistivity in the horizontal direction, resistivity in vertical direction. Divide the vertical by horizontal, you get an isotopy ratio. This will be equivalent or synonymous to your VPVS in seismics. When you look at it, it tells you a zone that is most anisotropic below the moho. That dark line there, that line is the crust seismic base moho. So this steep feature there, that is subcropping at the Northwest Borneo Trench, is anisotropic. That is a direct channel to the mantle. The heat is basically being contributed from a mantle source. That's what is happening here. In Sarawak, the same thing. The heat is being contributed from a mantellic source. In areas where you have lower heat flow, we don't have that conductor. Although it has a nice seal. You can see the conductor seal there. In offshore Sarawak, you look at that again, the most high heat flow area, the anomalous area there, that polygon green is the same as that. So we do have the blues. This will be a heat at the top, whatever is producing the heat. And it's overlain by very deep Bungaron Trench, Bungaron Trench is somewhere there, very deep sedimentary basin. You have lots of sediments covering it. And therefore, we have a system that is capped very well. So that's a heat source for your petroleum system modeling, geothermal modeling, and anything that you dare to ask. The beauty is this phrase, sustainability. Is it sustainable? It is sustainable if you can find a geologic feature that links it to deep origin. It is indeed mantellic. It's of mantle origin, and therefore it's sustainable. So if you're going to produce anything here, you are assured of continuity. That is what we actually are looking for in the new energy. So when you are talking about new energy initiatives or meeting the global requirement for 2050 net zero emission, you will come across sustainability. So we can't sustain this geothermal or hydrocarbon system if we understand the deep structure, and we do now. So now discussions, question and answers, and basically I want to have the opportunity for students or researchers to actually understand the current thinking in this energy transition period. And I'm also keen to continue to develop postgraduate students. I've done that all my life, to build collaborative research and guide young ones to actually produce things that will help us save our planet and make it safe to live. So Sarawak images I showed you. So I take the anisotropy ratios. I told you that we have mantle origin. You could actually see Masla Maidon and Jung in 2022 published a map showing the distribution of CO2 in the gas that was sampled in exploration wells throughout Sarawak Basin. So that's your CO2 concentrations. The red means high concentration, green means lower, and then blue is zero, no CO2. What is driving the CO2? It's very apparent.
These are images going down 200 kilometers. That line there is the moho. So below the moho is an anisotropic feature and is interacting with the crust above it. And that's what is basically leading to this area where you have huge concentrations of CO2. So it's like a truss system. So any basins, anything above it will be filled or charged with CO2 contributed from mantle. There will be other sources, but there is a component. If we are expecting hydrogen, that's where we should be, because they are coming from this mantellic source, and therefore it is sustainable. If you look in this paper, if you don't have it, call on me, email me. We actually outline the procedure for exploring for geologic hydrogen. And that procedure is also applicable to geothermal exploration. It's important that we start to think in this way, because that is the way the business is going. Sustainability. How do I balance my CO2 emission to get carbon credits? This is it. You need to understand the structure of the ground. How do I find favorable areas in Sabah to prospect for geothermal energy? We've done marine empty. You can see that we're picking up a lithosphere, overlay it on geological map. You see your ophiolitic rocks and melanges up in northwest Sabah. This zone here in yellow with purple things, those are volcanics, Mesozoic intrusives. It's underlain by mantle that is very resistant. There is a shear zone or a cap. So those could be intrusives, mega intrusive. Green here is ophiolites. Those are boundaries interpreted by geologists based on outcrop geology. There is a change in the lithosphere. The crust or lithosphere is thickest within this band. So this is your magmatic arc. And therefore, if you're looking for granitic areas where you have your geothermal, it will be in this belt. That is the implication. If we look at the anisotropy distribution, we can also work out areas where the old or pre-existing structures are being reactivated. So you have hot water, hot fluids flowing in certain areas. Those will be these areas that I've marked out here. If you compare them with the sediment thickness map of Maslam, Medon, and Jung, you will find these linear zones that are filled with thick sedimentary materials. So it's telling you that we have compressional deformation. So those are zones where we have compressional deformation. So this lithosphere is being compressed because you have your Java subduction zone here. You have your Eurasia coming down from Indochina plates coming down here. You also have your Philippine sea plates and the Pacific plate coming down. So this area is being compressed from all sides. And what is happening here? The lithosphere is buckled. So it goes up and down, up and down, up and down. And those areas where it is up are where your thermal sources will be. So that's how to think of future. That's where to go future. One of the things you need to do for the benefit of geologists, you would have heard about Mackenzie model, about Venick model, or Lister model. So when you do your MT experiment, you want to interpret heat sources. This is an image across the Rift Valley, Kenya Rift Valley. The earth is splitting in Kenya Rift Valley, and we have lots of volcanism around. And you have geothermal fields or geothermal fields. So we had measurements, 1994, my PhD student. So we have a transect cutting through the Rift Valley. You could see this conductive clay cap, and you have an intrusive body here. This is the axis of the rift, but we have off-axis intrusion, and that's where the volcanic fields are, paleo hills. So where will I drill? It's here. It's not here. It is here that your heat source is, not there. There's another
intrusion here. Those are the bounding areas, or thermal or real, the geochemically altered envelope, mineralized, highly mineralized shear zones. Joint inversion was done, gravity and magnetics, by Abdel across another transect, and using cross gradient. So on the left, you have resistivity from MT, density. You can see the features mapped by gravity and MT are similar, exactly similar, because of cross gradient. It makes life easy. So you can tell where your conductors are, where your resistors are, and you can make decisions where to drill. That has a cap. That's your cap rock. So I can drill into there if I want. So that is what you should be doing or thinking of. Now, you want to answer the question here, where is this heat source? Remember Mackenzie's model, the heat source is sitting at the center, just below the basin. In Venick model, simple shear model, the heat source is offset from the basin. You have a major detachment, and all the faults are actually solving into this detachment. The heat source is away, so you need to identify where it's not here. Lancaster modified two models and came up with this one. That's where the heat source. So you need to know which model is applicable as a geoscientist. In this case, it is the Lancaster model. And where will you find natural hydrogen? Things will seep from the mantle, or CO2 will seep all along from the mantle to the basin over there. That is how to do it. So, in Kenya, I ask you again, where is the heat source? I already interpreted this image. I put in detachment zone and all the faults that are listed, sub-grabens, half graben or rotated grabens, and the capping rocks. And the same thing applies to our MT line. If you look at this image, that is similar to that. Basically, nature works in a particular way. This is a granitic complex here, Migori Gold Belt. So these areas have been impacted on because the ground is deformed. So look at how this blue is down, is up, is so the Rift Valley formed in a pre-existing system, a fracture zone, ancient shear zone, because the ground is being, we have Indian Ocean pushing against the African crater. And that broke it. So that's why it's rifted. Brazil, Paraná, Etendeka basalt, largest flood basalt in the world. Show you an empty line from there to there, crossing the entire Paraná basin. What you see, this is the image, going 100 kilometers. You see this cap rock, cap, and you see this blue intrusive or basement domain is fractured heavily, and below is a detachment. So all those are listric faults that actually sold into this detachment, which sold into a heat source. What model is applicable? It has to be Lancaster, or at best, Venick model. So you need to be able to know what model is applying in your area of geothermal interest. If I enlarge the top 15 kilometers of this image, it looks like that. You can actually see the sediments and then the basaltic intrusions. Because you have, these are sails, but you have dikes. It's a dike. So that's the heat source. It has a nice cap. And so is that one, and so is that one. So that's how I use my MT to interpret geothermal scenario. Capability development. I believe in educating young ones. I believe in knowledge transfer. And once in Petronas, I made effort to train people. Shahir did his PhD at USM in Penang under my supervision. And I downloaded multiphysics knowledge to him. And Alvin Kapia, also one of my previous workers, and I'm the CG worker. We collaborated. All these are, you train people. Not just in Malaysia, I do it for Brazil. Maure at a postdoc in Brazil, Sergio's team in Brazil. I work with them to develop talent. And we need to do that for our future. We need to continue to train young ones because that is our future. So I thank you for listening to my talk. And I look forward to collaborating with you guys in future. And please feel free to send me an email. And if you have any issues that require attention, I'm happy to look at them at cost. And for those who are numerically inclined, I want to learn this technology, I would recommend my SCG book. I have a copy, electronic copy, if you can find it in Amazon. So you can actually read it and understand the basis of these technologies that we're talking about. So thank you. I'm open for questions. I really am open for questions. Thank you very much, everyone. And please ask your questions.
So, okay, ladies and gentlemen, if you have any question, please unmute and then can give your opinion, and also, of course, you can ask from Dr. Max lah. Ya, Pak Yunus. Silakan, Pak.
Good evening, Dr. Max. Thank you very much.
Oh, hello there. Good evening to you. How are you?
How are you? Fine. Long time not to see you.
Same here. Same here.
Yeah, it was very interesting talk today, and I enjoyed your presentation. Okay. One thing related to the first related to the result in Sabah. Did you do drilling there, and what the result? Is there any confirmation between drilling data and then electromagnetic data?
Yeah, very good question. There are wells. It was done for oil exploration. And when you drill a well, you measure the bottom hole temperature. So the temperature data for hundreds of wells were available. And that's what Maslan Maydon and Jung compiled the data and produced a heat flow map for the region. And so that becomes like a test. If I cycle back to so that heat flow map becomes a test for any method. So we ran MT over it, and the heat flow measurements are already there. We know what the temperatures are. We didn't use that in inversion. Inversion was done separately. But you confirm that the anomalies that you see in your MT are consistent with the heat flow measurement in the area. So in a sense, we ground truth it. So that's the ground truth. So there were wells already in the area. Offshore, we have no wells, but you can make an assumption that if you predicted an anomaly in the sea where we have data and the overlies temperature anomalies consistently in Sabah and Sarawak, if you apply the same method on land, you'll be able to actually find heat sources. So it does work. There's no question. I have many examples. I didn't, because of time constraints, I have from a lot from Indonesia, actually. But I will show that maybe in another presentation, another meeting. Most all our work are validated by, we do our invention and we validate our models using well data. So if your residuities are not fitting the well residuity, the models are incorrect. So all our cross-gradient models actually match well data, and that's the greatest happiness. And this is echoed by papers by Max Morcam and co-workers who also do this kind of thing. And they looked at the resistivity and velocities from cross-gradient, compared the well logs from many places, many basins, and they concluded that actually it fits the well data. So it's the best, to me, is the best method for inverting remotely sensed data. If you don't have any control, any wells, use cross-gradient.
Okay, thank you, Dr. Max. Dr. Hariri, can I have another question?
Please.
Okay, thank you, Dr. Max. Concerning the data from Kenya, I think, yeah?
Yeah.
Could you show again?
This one or the
no, some cross section with some like blue block cross section.
Are you not seeing? Okay, let me see. This one?
Yes.
This one. Yes. Yeah.
This is Paraná, Brazil.
Oh, Brazil. Sorry. Yeah.
Mm.
Okay. Yeah. My question is related to the. Okay. You have a couple of blocks there. Yeah. I'm thinking about the data quality. Could you explain about the condition of data quality? Sometime if we have data but disturbed by noises, something like that, and then okay, if we have clean up the data to be clean and genuine data, sometimes if we invert, we have some okay, some a certain data, but geologically, okay, it's difficult to understand.
Yeah, and
Is
I
this,
see the,
yeah, is this
okay,
figure? So my question related to what about the data quality of this?
okay, good question. Everywhere I worked on land, everywhere, I will collect DC resistivity, I will collect time domain EM, I will collect MT. I never collected MT data on its own. And that is what any institute, any collaborator that I work with, I make them collect all three. So in this place, we had CSCM, which we use to correct static shift, first of all. So the MT data are broadband, they are good quality data sets.
Okay.
And using the LIMS system and the geometrics model EH2. So the data have been collected using standard, very well-known academic equipment. And the TEM system is Cytotherm Mark II, I think Cytotherm Mark II-B or 3. So for which we collect central loop and coincident loop time domain EM. So we use the central loop to correct the E polarization, and then the coincident loop to correct the B, the TM, transverse magnetic. So a lot of, I get them to do a lot of things before they even begin to model. So this data were, it's called conditioning or homogenization. I will not model data that wasn't correctly homogenized. And I have DC resistivity on top of it. So the top 5, 10, 20 meters is constrained by DC resistivity. And then from 10 meters to 200 or 300 is constrained by TEM, time domain EM, and then MT. So MT kicks in. If you don't do that, you are wasting your time. You have to combine time domain EM and MT. So if anybody thinks they can get it from MT alone, they're joking on land. I am telling you this, I've done it for 40 years. So my recommendation is that your question is very right. You think about the data quality. It's supreme because garbage in, garbage out. So once you clean your data, you already know the solution. You can see it in the results. You can actually tell what is happening from the data. Once cleaned, you know that you got a big reservoir, a big target somewhere. You know it from your data. But yes, very relevant question. Please do not be in a hurry to press a button and just use data that was available. Please think about the data quality. One is cleaned up correctly, everything falls into place. Then you can talk about geology. And then you are bold enough. You read my papers, I'm bold enough to challenge seismic. You cannot do that when you have noisy data. So it is the fact that I combine so many things that I can say, look, I believe my results more than seismic, or I accept what seismic says. If not, I disagree with seismic. I'm the only one in the world that does that. And I do it in impunity because I have good data. So please, for any student, any researcher, there's nothing like good data. Once you have good data, you solve the biggest problem.
Sure.
You have solved the biggest problem.
Sure.
Please, good data always. Garbage in, garbage out. Don't tell me that machine learning and all those things will find things when you have garbage. You put garbage in, you get garbage out. It's as simple as that.
Yeah. Okay. One more thing, but this is short only. A comment related to the Darajat geothermal field in West Java. Yeah, actually, okay, there are many wells there, and I think this is very useful to compare between a geophysical imaging and with the well data. And my team, did also MT and graffiti and compared to the well, the well that successful and the well that are not successful, and compared to the MT result, graffiti result, and what look like. That's very interesting. Okay, thank you. Thank you.
Yeah, thank you very much. Yeah, I look forward to seeing some of your data. I'll visit you and we'll look at some of those results.
Yeah, thank you.
Thank you very much. Robin?
Yes.
Robin.
Yes.
Hello. Yes, hello.
Hello.
Dr. Meju, Dr. Hairi, thank you for organizing this talk. This is most, I had said earlier, most intense. This cross-gradient multiphysics is not just multiphysics, but also combining geochemistry and biology, bacteria population count. It's intense, really. Earlier on, Dr. Meju, you mentioned about this source rock, cap rock, and for oil and gas, you must have this cap rock that completely seal the oil and gas, and also these gases, the hydrogen sulfide, carbon dioxide, methane, and there are companies actually this gas being produced, this hydrogen sulfide, carbon dioxide, methane, they pump back into these into the rock. They pump back. And actually, my friend in Barrow Island in Western Australia, he's what they call this environmental scientist. He monitored the carbon dioxide being seeped out from this oil and gas reservoir. And what he did, he actually pumped back this carbon dioxide into the rock layers. But most interestingly, you mentioned that the seal, the cap rock, must able to contain the carbon dioxide for at least 100 years.
Yeah, that's a Kyoto law. That's a convention agreed with.
Yeah, there's a convention.
Kyoto. Yeah.
The thing is that we can determine whether the cap rock is fractured. But how do you determine?
You can't. Okay, that's a good question. It depends on the depth, so the cap rock. So if the MT that I showed you, CSCM that I showed you, were collected every 3,000 meters, 3 kilometers. So it's spatially aliased. If you collect CSCM and MT, denser spacing, like I've seen in Malaysia, when I was in Malaysia, Newfield collected CSCM every 400 meters. And the result was amazing. I have the image. So you will see where the cap is fractured. You can see it in seismic reflection because the cap, well, seismic measurements are the hydrophones, the receivers are towed every 6.25, measurements are made every 6.25 meters. So you have very, very fine sampling. You will see it. You don't have to be perfectly sealed. It's almost impossible in nature. There will be cracks. Things will be coming out. So you have micro seepages. You also have
Yes.
macro seepages, so micro and macro. You want to avoid macro seepages. For micro seepages, you can live with it. So, but what you tend to do is, if your reservoir is fractured, it's because you're drilling in a structural high. So your structural reservoirs is like an anticline. It was compressed and therefore it fractures along the axial areas. What you want to do is find an aquifer off the axis and then bury your CO2 in the aquifer. So you want a stratigraphic trap where you have sand lens encased by shale or clay material. That's a better place to bury your CO2 than putting it in a crestal, oil field that the crest has collapsed. Basically, you're pumping in a balloon that is punctured. You will never pump that balloon. You will never go up. That's what it is. Don't put it back if it's fractured.
Yes.
So
And
we can interpret it. And the other thing you say, how do we interpret it? If you do seismic inversion, normal conventional QI inversion or CSEM inversion, the cap rock, when it's fractured, your CO2, methane are rising. If you have iron in the water in the environment, any sediment bearing iron, you deposit pyrite, iron sulfide. So pyritic alteration happens along the crestal path, and therefore the velocity will be enhanced. And then you have other minerals like calcite being deposited, so classification. So you have increased density, increased velocity, increased resistivity somewhere in those areas where you have dense fracturing. So what we do is that we will do an isotropic CSEM or MT, not isotropic, so that you measure the resistivity in vertical and horizontal directions and use that to determine where the fracture is. I purposely showed you sections in Borneo, snippets, where it's that way. Let me show you. If you actually calculate the ratio of the vertical resistivity to the horizontal resistivity, you end up with what we call the anisotropy ratio. They will be high where you have deformation. Fracturing, if the fracture is sealed, it's not a problem. If the fracture is open, that's when it's a problem. If the ground is moving, it's being sheared, subsiding, then you have anisotropy developed. You can see that using a combination of CSEM and seismic. So we can see that, definitely. But my recommendation is that you look for aquifers that are stratigraphic, that is encased totally by shale. It's not built by as a structural high. And that's where you bury your CO2. That's what you do.
Yes.
That's the safest way.
Yeah. So we can determine these micro and macro fractures in
we can
the.
No, we can infer the presence.
You said by using a seismic refraction?
No refraction, it's a reflectivity method.
Reflectivity.
But another way you can determine it.
But the thing is that how do you determine the at least 100 years? Do you have any idea?
No. If you prove that it's sealed today, you meet the Kyoto requirement. So if it's sealed today, that thing was not formed today. It was formed over 100 years ago, over 1 million years ago. So you assume that if it's sufficiently thick, so you're not going to break it by pressure from pumping, you have met the requirement. So you're ticking boxes. So the box says, is still okay for now? Yes. Will it be durable for 100 years? Well, maybe, most likely. So we cannot tell, it's calculate, but we can infer that it's sufficiently thick, and therefore we meet the Kyoto criteria. So it's a bit of a political thing. But we play between the lines. So we're business. We run a business. We have to run a business, and the government wants us to meet certain things. We meet those things. So your data assessment manipulation says that the cap is intact at the current time, and the resistivity says that it's homogeneous at the current time. Therefore, the cap is intact. If you want to even go be more exotic, you could do measurement of something called SP, spontaneous polarization. That thing shows leakages. When you're looking for cracks in a dam, in a bridge, you do SP. So if you run SP across your prospect and you don't have SP anomalies, that tells you that there's no weak zone that could cause any danger for now. So basically, the geohazard element is been met. You tick a box. So spontaneous polarization, electrical resistivity from CSCM and MT, your seismic reflectivity. Those three will tell you that the seal is in, it's got good integrity or not. And therefore you tick a box that you've met the Kyoto Convention requirement. And then you start to put in your CO2.
Yes. Thank you, Dr. Meju. My second question is that you mentioned about Dr. Mazlan and Jong's work 2021 in the Sarawak Basin. Yep. Also, you mentioned about this where the potential area where we can get geothermal energy in Borneo, the volcanic zone,
yep.
And also in Brazil, and in Africa, the Rift Valley. But
yep.
Those areas, the Sarawak Basin, in Borneo, volcanic zone in Borneo, and the Rift Valley in Africa, in Kenya, and in Brazil, the salt, they are actually deep. They are 10 to 15 kilometers of sediment. And for example, in Borneo, the volcanic zone in Borneo is 5 to 8 kilometers, this heat source.
Yep.
So the thing is, we are looking for geothermal energy to set up a geothermal electric power generation. How deep actually we have to go? What's the point of view? What's the point of view giving example, the Sarawak Basin, the sediment thickness is to 10 kilometers, Borneo to 5 to 8 kilometers, and Brazil 15 kilometers. So,
okay.
Yeah. So
that's a good. That's a very, very good question. If you see, there's a slide I just put up. It has at the bottom right-hand side sustainability.
Yes.
To meet the Kyoto thing, you have to demonstrate sustainability. That is, it's geologic. So if you're taking it from 200 meters, how are you sure it's sustainable? It's an aquifer. You pump water, after 1 year, it's all gone. The water is finished. There's no heat. It's not sustainable. So in this new energy transition, the word sustainability is so important. And don't forget, I come from an oil company background, oil and energy background, where the onus is on the oil industry to prove that it's not a polluter. So we are looking for things that are sustainable. If you're looking for mineral deposits, you're going to mine the top 400 meters. But the minerals didn't come in the top 100 meters. They came from basaltic, from igneous stock that is 1-2 kilometers deep. And by the way, in these basins, these wells are 3,000 meters, 4,000 meters deep. All this, the bottom hole temperature, this data from Mazlan Maiden were collected from wells that penetrated all the sediments down to about 4,000 kilometers. So we're not looking for water at all in the 200 meters. That area is of no interest to anybody. For the benefit, if you're looking for what's going to be sustainable, you need to know that there's a deep source. So whatever you see on the surface, you may have your wells at 100 meters or 200 meters, but you are comfortable, you are sure that it has a link at depth that is coming from the mantle. Therefore, it's going to last long. It's not going to be 2 months and it's finished. That is the meaning of sustainability.
Okay, yeah.
So you have to have a big look at the big picture.
Yes.
So you zoom in, and that's the way to deal with politicians. That's the way to deal with governments. That's the way to deal with the environment. Sustainability.
Yes, thank you, Dr. Meju. And to Dr. Hairi, this is a good opportunity to get a PhD student to do this exploration for geothermal energy using this cross-gradient multiphysics.
Yep, I agree.
Yeah, it's very intense. You combine resistivity, seismic, gravity, radioactivity, magnetism, combine everything, and you use this mathematical model for your cross-gradient analysis. Very accurate, amazing.
Thank you very much. Thank you very much.
Thank you, Dr. Meju. Yes.
Thank you, Miriam.
Hello, sir.
Hello. Go ahead.
Yeah, first of all, I would like to commend your effort for this talk and Dr. Henry for organizing the talk.
Thank you.
Yeah, my question is on data acquisition. Based on this cross gradient, is the data supposed to be obtained simultaneously or different, or is there a specific equipment that will get all the recordings at the same time? And the second question is about the software you made mention, which I wasn't clear about. Thank you, sir.
Okay. Good, very important question. The first one, if you're doing three-dimensional work, that is 3D measurements in an area, it doesn't matter. You can acquire them in different locations because you're going to look at the volume, 3D volume, a region, like the one I'm looking at now. They don't have to be acquired at the same time, but it makes sense to acquire data in the same area. But if you're doing 2D line, one single line, to use cross-gradient, you must make measurement along that same line. That's the only condition.
Okay.
Now, for shallow work, land environmental work, equipment available, there are systems that allow you press a button, you measure electrical measurements. When it's finished, you go to the software, change the settings, it becomes seismic, you press a button, you do your seismic. So there are systems for that allows you to do multiple measurements already. A case in point is what you can get from KMS technology in Houston. You also have geometrics, they have model EH4. So it's a control source AMT. You can use that same equipment. I had it when I was in the University of Lancaster. You can do seismic using GeoIntel, their recorders. So I normally will do the same, I'll cover the same area with different equipment. But you don't have to necessarily do that for 3D work. For 2D, yes. For 3D, you can do that. Now, software-wise, for oil type of work that we do or mining industry, you can imagine the diagram you're looking at here. These lines are hundreds of kilometers long, 100 kilometers long. We're making measurements every position along that line. And when I come to model this, I will describe the whole of Borneo land and sea with 20 million cells. So I'm going to running the mathematics on 20 million cells. That requires a huge memory supercomputer. And the software that the industry knows, I've used in the industry, I contributed knowledge to, is RLM3D. It's marketed by CGG Multiphysics in Milan. It's available up to share for rental. And they actually, if you're in academia, they will install Geo tools for about $295 for academia. $295.
Okay.
That's not less than $300 for academia. That's a special price. So yeah, the Geo tools that allows you to build these models. If you don't want to run big projects, you can also then go to take the job as like a batch job and run in Milan cluster if you want. So the software to build the model, the interface, do an empty work, gravity and all those things, get it for about $300 as an academic establishment. So you get a license for that. And there are various other software. I have my own software. And so if you know, it depends on what you're looking for, you can always contact me anyway.
Okay.
Okay.
Yes, sir. Thank you.
Okay.
We look forward to more of this lecture.
Okay.
Okay, well, well, Max, thanks for your detailed talk.
Thank you.
My question, you know, is on mineral exploration. Will multiphysics, you know, can we use that to isolate specific minerals? By that I mean, it's not just having anomalies and, you know, that will identify mineral bodies, but being able to say, okay, what we're seeing here is iron ore, or, you know, gold, or, you know, just specifics, you know. That's one question. Then the second is cost. You know, what's the cost like? I know if you mobilize a fixed wing, you know, airplane to acquire data, it may cost a lot more. So generally, you know, how is the cost like? You know, looking at equipment that needs to be mobilized, you know, to do like mineral exploration work over an area. You can just give a general idea. You know, it may not just be the entire country of like Nigeria. You know, it may just be a subset. You know, just a small area, maybe a state. So isolating specific mineral and then cost
and cost
to mobilize. Yeah, thank you.
Yeah, thanks. Interesting question. Those two questions, the answer is straightforward. The images I showed you here were drawn from regional studies. So these are what we call reconnaissance surveys. So the reconnaissance, we map out big, and then you do specific, you home in on a prospect. So you choose a basin, you select a play, prospect, and then when you're on the prospect scale, you change the geometry. Then you need to drill. You don't drill based on these regional studies. You drill based on the next set of high resolution studies. I will be deploying transient EM, for instance, to distinguish between massive sulfide and disseminated sulfides. The disseminated sulfides basically are nodules encased in silica, and therefore you use induced polarization, IP. So that's when you deploy IP. So only IP responds to disseminated minerals better, where you look at the chargeability and the frequency effect, percent frequency effect. If you're looking at massive sulfide, metallic mineralization, iron ore is transient EM that you will use. No other method. It's transient magnetics. So the diagnostics is well established. The mining industry actually lives on it. So it's just that now we have the software to be able to combine transient EM, induced polarization, magnetic. If you're looking for platinum, chromium, it's high resolution airborne EM, time domain EM, and magnetics. Because the banded ion formations, all those things have specific magnetic anomalies. So what you're seeing in this geograph is a general thing, it's a reconnaissance. So exploration cannot be done in one stage. You do the regional stage, intermediate stage, specific stage before you drill. That's where you name the mineral. You name, is it oil? Is it gas? Is it chromium? Is magnetite? All these things have their genetic signatures. So we know that already. We can fingerprint minerals. We can fingerprint our resources. So it's a question of budget. So money is the hindrance. If you put money on the table, we can fingerprint and tell you specifically what's there. So that's how the multiphysics applies at all scales, from micro to macro. But I've shown you the examples that I've worked on, which are the regional scale. So yes, cost-wise, they're not expensive. It's the same thing that the mining industry has been using for years. Airborne would have been done in everywhere. Nigeria has airborne done by Fugro many years ago. Malaysia has airborne data. Everybody in Indonesia has airborne data. So aeromagnetic there, not only there, you also have satellite imagery, which is free, available from NASA website, or you go to University of Scripps, in one for European Space Agency, you go to Norwegian Technology University and download the gravity and magnetic. So all those things are there. So we already know the regional. You can look at those free data sets, pinpoint an area, and then select your field area and go in there and deploy the right tools, the multiphysics tools to pinpoint, genetically finger point what you're looking for. So yeah, your questions are relevant, but the answers are yes, we can operate on any scale. And they're not expensive.
Thank you.
What is expensive is a seismic reflection CSEM, because to mobilize the boat from Norway to Malaysia is $2 million. That's the boat, not the survey. And then to mobilize aircraft from UK or Canada to Malaysia, you pay another $1 million. So that's what makes it expensive. If these days you don't actually, you can do your airborne magnetics and some other things using a drone. So you can build your own drones. That's the future. You do your drone to cover a small area, a small patch. So things are moving on, things are improving. Drones, geophysics is coming up.
All right. Thank you very much, Max. Thank you.
You're welcome. Any more questions before I? So thank you all for. Babu, please go ahead.
Yeah, please go ahead.
Thank you, Dr. Meju. It was great listening to you. My question would be again on the geothermal side, because of is there any method which also determines how the gases at temperature can be measured, like which direction they are flowing, or what is kind of the directional flow of the gases, especially in the geothermal industry? That's what we want to understand. Is there any method which can help us extrapolate that as well, especially if we have time domain information? Thank you.
Okay, very good question. When you talk about flow, it's something that you're talking about transient phenomena. So the only geophysical method that senses flow is SP, spontaneous polarization. To have ionic motion, ionic flow. When trees suck nutrients from the soil, I've done it. You put ISP around trees, you actually can tell when it's feeding. So when you have flow or leakages in a dam, any dam construction, it's SP. That's the only geophysical method that monitor flow, no other one. However, the other methods, if you repeat measurements for different times, have what we call 4D measurement, time lapse. So by looking at multiphysics results this month, another 6 months, and another 6 months, you take the difference between them and tell where things are moving. That's 4D. So yes, you have two methods. Either you go for SP if you're on land, it's cheapest, or you do 4D of the other methods, 4 dimensions. So you repeat 3D every time.
Is there any depth limit for this methods? Is SP any SP method, like how deep we can do this?
I've seen SP done by Andre Reveal down to 10 kilometers for volcanoes. More looking at volcanoes in different parts of the world. So SP can be done, and it's cheap. You need just a digital voltmeter, costs £20, $30, and cables another $20. So for under $100, you have an SP equipment. or you need to buy porous pots, which are £5, £5. So for $100, you have an FP equipment. It's not expensive. People may think it's expensive, it's expensive. It's not. You can build your own system easily.
Thank you, Dr. Meju. Thanks for your information.
Okay, you're welcome. Okay, if any more questions, I thank all of you.
Dr. May, I think this is last chance we give to our participant because it's almost 6:30 here. So last call. Any more question?
Yes, sir.
Yeah, please proceed.
Go ahead.
Yeah, thank you. Thank you very much.
Go ahead.
I'm Dr. S.L. Salawo calling from Nigeria. And I've been...
Thank you. Hello, we lost you. Hello, we lost you.
Hello? 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 Hello?
Oh. Hello?
Yeah,
hello? Okay, you're back now.
Hello?
We can
Hello?
hear you.
Can
Yeah,
you
we
hear
can
me?
hear you. Yeah.
Okay.
Yes.
Now, you see, this is a very insightful presentation. And from all indication, we must have gotten data in some places in Africa, especially Nigeria. How can we key into this such that it will help us to bring up the sustainability development of our mineral resources? I'm just thinking, can we go back to the archive to recruit all those methods that have been used before, especially in the oil sector, relate it with that of the mineral sector? How do you give us the background? Because developing countries need this modeling than any other place. That's just my own contribution. That's how do you help us?
Yeah, I would say that send me an email as well. So
okay,
that,
okay.
I'll be able to, we can do this offline.
All right.
But basically, all the geological surveys in the world, we have data for mineral exploration. I know that Malaysia Geological Survey has one, US Geological Survey, Nigerian Geological Survey, I think it used to be in Jos, will have the geophysics, gravity magnetic data sets, and then geochemical data sets. Yeah. And so there's a lot of data available. So it means going to basics, there will be there will be hard copies. So these days you have software available from GitHub that you can scan and digitalize those data so they become numbers that we can invert.
Okay.
So if those data are digitalized, then we're in business. We're able to take gravity and magnetics, apply cross gradient, take geochemistry, add to them, and all those kind of things.
Yes.
And that will improve the mineral base prediction. The oil industry is well developed in Nigeria. NNPC would have bottom hole temperatures for Niger Delta. Yes. There will be some other measurements done, and this will be available through an NNPC portal. And those will be something that can be combined with free gravity, satellite gravity, and magnetic data available from, and also from European Space Agency or National Technological University of Norway. So there are systems in place. It's just a matter of putting our heads together to tap into it. So what I would suggest is send me an email offline and we can take it. So there is hope. Everything is possible. Everything is possible.
Thank you. Okay. Thank you. I appreciate. Well done.
You're welcome. You're welcome. Okay. So, Professor, it looks like this is the last discussion. So thank you. It's been intense. I enjoyed it. If you have queries, I'm still I'll be able to respond to you on a one-to-one basis.
Thank you very much. Yeah.
I thank Petronas. Yeah,
thank you.
Thank you. I thank Petronas, who gave me 15 years of experience. I thank my friends, Dr. Hariri, who basically put this together and asked me to give this talk to GSM. And I thank all the support staff at the UKM who prepared a very nice brochure. So the poster was done in the UKM Bangi, and I thank them very much. And I look forward to continuing